First of all, thank you B2B for inviting me here for this webinar. Since the time is very short, I will be quickly going to the presentation point. I'm going to talk a little bit about the effect of aggregate quality on the performance of high performance concrete. But before I get into the real presentation, let me just quickly take you through the high performance concrete definition. But just to understand that high performance concrete is not just about strength. It could be any parameter which we are trying to enhance beyond what we generally have in a normal conventional concrete can be termed as a high performance concrete. So it could be concrete having a very high retention, very high workability, a delayed setting time, concrete with very high early strength, concrete with high ultimate strength. Some concrete may require high modulus of elasticity. Some concrete may require high abrasion resistance. And of course, the focus will always be on high durability and longer life in severe environment. So it encompasses a lot of various parameters to form what we call it as a high performance concrete. Having said that, let us now get into the real story about the aggregate. See, when we talk about the aggregate, the primary responsibility or the function of aggregate in concrete is to act as a filler. So basically, we add aggregate so that we will increase the volume. And the idea is that generally it will remain inert, not take part in any chemical reaction, though some aggregate do take part in chemical reactions. But the idea is aggregate is the most common thing that we add to concrete, and we should not bother so much about it. Generally, on the projects, aggregate is given the least performance when it comes to quality, and we try to buy the aggregate which is of the least quality, which leads to a lot of not only quality, but also commercially, it may not be a very good solution. So the million-dollar question here is it justified to spend more on a better quality aggregate, especially if we are going for a high performance concrete? So let us start the presentation with this statement that we save more by paying more. Let us see if we can substantiate this statement with some case studies. So a very quick look at the requirements of IS 383. There is a requirement for deleterious material. So if the deleterious material is more, there will be lesser strength, a lesser durability. If the aggregate crushing value, impact value, abrasion value is less, it means the aggregate is strong and you will have a better performance. If the soundness value is less, it means your aggregate as well as concrete will be more durable. Alkali aggregate reactivity, if it is innocuous, it means you will have a better and a more durable concrete. The individual and the combined gradings, especially when we are talking about the sand. If it is a river sand, the presence of silt and clay can be very detrimental. If it is crushed sand, very high fine or crusher dust, it will increase the water demand, it will reduce the strength, and thereby we will require more cement to get the required strength and performance. And finally, the combined elongation and flakiness. Generally, nobody looks too much at this, but this is also very important. If the EIFI is high, we will require more cement. It means more cost, more issues related to durability. Specific gravity water absorption, though there are no major limits specified, but if the specific gravity is high, it means the aggregate is strong and can be used for higher strength, higher performance concretes. Water absorption, if it is low, it means it is a better concrete. Now, having had a quick look at the requirements of the 383, let us again go through a few questions. Will all aggregates satisfying IS 383 requirement give the same performance? There is a long range, a big range between which the values will vary. But if I say that the aggregate satisfies the requirements of 383, will it give the same performance all along? Is it worth spending more to procure or to produce a better quality aggregate? And which parameters will significantly affect the performance of concrete? Let us try to find the answers to these questions through some case studies. In the first case study, this is a project where we had to construct a viaduct, and there were three sources of aggregates. One was about 10 kilometers, another 40, and third was 70. So economics says the source which is closest will be the cheapest, and we should go for that particular source. And that is exactly what the project manager wanted us to do. Now, if we look at all the parameters of the three sources, you will find that more or less they are all qualifying to the requirement of IS 383. But quickly, if you see, the specific gravity of source 1 is 2.61, whereas that of source 3 is 2.91. If you look at the water absorption for the fine aggregate, it is 4.8, very high here. Here it is around 3, substantially lower. Soundness, here it is in the range of 3 and 4, whereas for source 1 it is 10. They are all passing the requirements of 383, but there is a big variation. Now, when we did our mixed designs for an M35 grade concrete, this project also had an M60 and an M70 grades, but we started with M35 just to show the project manager what can go wrong. So when we did this trials with source number 1, we required 355 kg cement, 120 fly ash, and we had to add surprisingly 15 kgs of microsilica even to get M35 grade concrete, because the aggregate was so poor that we were just not getting the strength. The source 2 was a better aggregate as compared to source 1, and the cement contents reduced, and we were able to eliminate microsilica. Source 3, the aggregate was coming from the farthest. However, it was a very good aggregate, and we were able to reduce the cement contents substantially. Now, I will not get into the calculation, but just to give you an idea, if I compare source 1 and source 3, per cubic meter, I was spending 394 rupees more on the procurement of aggregate, because the cost of aggregate here is around 5.53, here it is 0.684. So I was incurring almost 400 rupees more for the procurement of aggregate, but because I was able to reduce the cement contents significantly, for the cost per cubic meter, I was able to save around 468 rupees per cubic meter. It's a big saving. The project manager was only thinking, if the cost is less, I should go for this. The cost of aggregate is less, I should go for this. But when we showed him this analysis, he understood that it's not a good idea to go for the cheapest aggregate. Probably we can spend more and save more. And again, you can see here, my target strength requirement was 47. Here I was getting about 50. Here I am getting 58. It means there is further scope for reducing the cement contents of the aggregate for source number 3. However, we stopped at this point and we used this mix. So if you look at the economics, the concrete requirement for the project was about 2 lakh. There was a saving of around 468 rupees per cubic meter, in spite of spending almost 400 rupees per cubic meter more for good quality aggregate. And we could get a savings of around 9.4 crores on a project, which is a very significant amount, and doing a concrete which is much more durable, having much better strength, less variation. Imagine if this happens for M35, what will happen for an M60 or a M70 grade concrete, especially when I have to pump the concrete to the range of almost 150 meters. Next, I will take a case study of another project, a road project, where we also had a tunnel in the project. And the muck material which was going to come from the tunnel was going to be used for production of the aggregate for concrete. Now, generally, basalt is a good aggregate. We get good properties. However, in this area, there was a weak basalt which is called as an amygdaloidal basalt. So if you look at the table below, the black rock is the very good sound rock, and you can look at the specific gravities and the water absorptions. And the green and the red are the weak amygdaloidal basalts, which comes in the range of around 10 to 15% of each blast that we take in the tunnel. Now the entire rock was coming together as one single muck material, and it was going in for crushing and for production of concrete. So now when we designed various grades of concrete from M30 to M50, project 2, these are the strengths that we were getting, and we had to use very high cement contents in this project. When we use the same mixed designs with the project 1 aggregate, look at the jump in the strengths that we were getting. It means I could have designed an M60 with a 63 requirement for something which I am designing an M40 with the bad quality aggregate. Of course, I couldn't get the project 1 aggregate on project 2 because it is too far. So that economics also needs to be taken into consideration. However, the idea is in and around your area, look at not just the closest and the cheapest, but multiple options, look at a better quality and do a proper cost benefit analysis and see whether it makes sense. So then what we did was we started manually, physically segregating the poor quality rock that we were getting and then crushing the remaining part of the rock so that we could get a better performance from the aggregate and we could lower our cement contents and do a better and a more economical job. Again, to give you an idea, on this project, an M50 grade concrete girders were there where we required 35 MPa in 2 days. The poor quality rock was giving me about 21 MPa in 2 days, and the segregated crushed rock was giving me about 40 MPa. If I had not done that segregation, probably I would have had to wait for almost 4 or 5 days to get that 35 MPa, and the cement contents would have significantly gone up. Again, it is a cost. So it would have led to higher cement content, probably would have had to use microsilica, and the waiting time would have gone up, which would have increased the duration of my project, again, which is a big cost. So to quickly conclude, lessons learned, the quality of aggregate, which is generally the most neglected part of quality control in the project, it has a great impact on the properties of concrete. High absorption value, silt content in natural sand or dust in crushed sand can be detrimental. It can reduce the strength as well as durability significantly. We should check the EIFI silt dust in all our consignments. We should conduct a cost benefit analysis for various sources and then come out with a final conclusion and not just look at the cost of aggregate only. Improving the quality of aggregate can bring a substantial saving in the concrete. Even if we find that there is no saving, it is a 0-0, still we should go for a better quality aggregate so that we will be able to consistently produce the concrete without any major quality hazards. With this, I am concluding the presentation. Thank you for the opportunity.
Thank you, sir, for shedding the lights on critical role of aggregate quality in HPC.